Hello, greetings, welcome to a ramble of mine that I hope can be helpful to the nations. I ramble about maths questions from past matric exams, and today we are inside IEB's paper 2 from November 2023, and we're looking at the second last question from that exam, which is question 12. Let's get into it. In the diagram, circle with center O has diameter AOC, thanks for letting us know, and chords AB and BC. Okay, so let's just see what's going on here. So we have our center O, and that is a diameter. And when I see a diameter, I'm immediately thinking angle in semicircle, right? So that's a 90 over there. I am immediately looking out for radii, although I only see AO and OC. I don't see any other radius coming out from O. So that's the first information. Well, let's highlight the first information. There are how many informations? Anyway, just going to highlight that is a diameter for myself, in case I need inspiration at some point. Right. And then the next point says chords AD and EC intersect with F with OF perpendicular to EC. Okay, so we have AD and EC intersecting at F, and OF is perpendicular to EC. So they've indicated that information to us on the diagram. So immediately I'm thinking, okay, OF perpendicular to chord EC, therefore EF and FC are equal. That might come in handy at some point. Okay, cool. And then let's proceed. AOC bisects BCE. Where is BCE? BCE. So this angle. AOC bisects that angle. And I'm guessing the reason why they haven't indicated that on the diagram is they're expecting you to know what that means. So bisects mean it's split it in half. So this angle A2 is equal to A1. So just going to draw a little bollocky over here and over here to remind myself that those are equal. That is information that has been given to us. All right. And then, of course, state all relevant reasons with your statements. And the first question that we are asked is to prove that triangle ABC is similar to triangle OFC. Okay, cool. So, similarity, more often than not, I would say like 9 times out of 10 times, when you need to prove that two triangles are similar, you are most likely going to need to show that their angles are equal, as opposed to showing that their sides are in the same proportion. In this case, I can see straight away that, well, they've given us that those two angles are equal. This is a 90, that is a 90, as we saw when we were chatting about the diameter over there. And then because of angle sum, the last angle, the third angle, must be the same in both triangles. Right, so let's do that. So we will say in triangle ABC and triangle OFC, okay, we know that angle C2 is equal to angle C1. It is given. Right, it's given to us by this little piece of information here. Right, then we know that angle B is equal to 90 degrees, right? And that is because angle in semicircle, right? And so therefore angle B is equal to angle C1, right? And then finally angle A2 is then equal to angle O2, and that's because I mean, you could say angle sum, but I think it is acceptable to say third angle, pretty much saying if the other two angles are the same, then the third one has to be the same because of angle sum. And so therefore, triangle ABC, okay, we've covered all three angles, is then similar to triangle OC. Yay, what's going on here? Okay, I've mislabeled something. Okay, it's not equal to C1, it's equal to F1, silly Billy. Okay, F1 is the 90 degree, not C1. Okay, so right, it will be equal to OF, well, not O, equal to, similar to triangle OFC. Okay, right, just erase these little dots before we think they have meaning. And the reason there is angle, angle, angle. All right. And I'm not really sure there's another way to go about it, I mean, or a shorter way to go about it. I think that's pretty much, yeah. I'll see if the memo says anything interesting. Right, so let's just start by filling in what we have uncovered. So that's a 90. Those are equal. And we also now know that triangle ABC is similar to triangle OFC. Okay, cool. So we're asked to determine the numerical value of BC to FC. BC to FC. Okay, let me not choose that. Let me use, so, oh, we also know, I mean, do I really need to highlight? Oops, but I will do it. This is a diameter. Okay, so we want to find the ratio of BC to FC. Okay, cool. So I mean, the key thing for me, what stands out is, okay, what information do I know about the sides in ABC and OFC? We obviously haven't been given any numbers in terms of, you know, this is how long this side is. So as I was highlighting my diameter again, it just struck me that AC is part of the bigger triangle ABC, and OC is part of the smaller triangle OFC, right? So if we just set up our, I don't know what you guys call it, but I call it my statement of proportion. So that's when you look at this statement and you use it to indicate which sides are proportional to each other in the two triangles. So you say AB over OF is equal to BC over FC is equal to AC over OC, right? And so what we see there is that AC and OC are the pair, right, that goes together in the two triangles. So we can then figure out the ratio of BC to FC by looking at the ratio of AC to OC, because that will be a constant ratio for the different corresponding pairs, if that makes sense. So let's say let OC equal to R, right, because it's a radius, so it's R units long. Then we know that AC will be 2R because it is a diameter. So let's say diameter equals 2 radii. Right. And so therefore, AC over OC is equal to 2R over R, which is 2. And so therefore, the ratio BC over FC is equal to 2 over 1 as well, not 2 over 1. Well, I mean, it is 2 over 1, but I don't know why I decided to write just 2 over 1. Will also be equal to 2. So BC to FC is just the same as BC over FC. That ratio is 2. And I'm guessing by saying numerical, they mean you give it as a number, so as a 2, as opposed to giving it as 2 to 1. I don't know if that would be wrong. I don't know. We shall see what the memo says. And I just forgot to say one thing here, right? This statement, you should indicate that you know this because A, B, C is similar to triangle OFC. Okay, maybe in fact I should just check the memo before we go to the last bit. So for the first question, third angle is a valid reason. Good to know. And for the second question, okay, they did actually give it as a ratio. So that just means that BC to FC is the same as 2 to 1. Okay, all that means is whatever the length of whatever the length of FC is, BC will be twice that. All right. Cool. So on to the last question. Again, I start by highlighting what I know. That is a 90. Those two are equal. We also know that triangle ABC is similar to triangle OFC. And we also know that the ratio of, how do I say this? I'll say the prop factor is 2, right? So the relationship between this triangle sides and this triangle sides is this triangle size will be twice as big as this triangle size. Okay, right. So let's see now the last question. So it says, hence, prove that AC over 2 squared minus AB over 2 squared is DF times FA. Okay, where is all this stuff? AC over 2, okay, which is just the same as OC, minus AB squared, AB over 2 squared, so AB over 2 will be the same as OF squared is equal to DF times FA. DF times FA. So, I mean, what immediately stood out for me on this side is, okay, AC over 2 is the same as OC. AB over 2 is the same as OF. And so it was kind of giving Pythagoras, so kind of telling me, okay, OC squared minus OF squared is equal to CF squared. But then there was a plot twist. On this side, we don't have CF, we have DF times FA, which is hinting to me that, okay, the product of these two is probably then equal to this squared. And I mean, we know from, I'll just do it in gray so that I remember that we need to prove it when we write on our answer. But we know that, okay, we have this line coming from the center to the chord and meeting it at a 90. So these two are equal in length. Yeah, I'm not sure, hey, DF na FA, bangena kanjani. So I'm just going to settle down onto my haunches. Is that a word? Haunches. So I mean, if I were to draw this in, right? If I were to draw this chord DC, this would also be a 90 because angle and semicircle. And I don't know what that would do for me, but it just seems significant. Yeah. So this angle over here would be 90 degrees minus dot, so that this and this and this can add up to 180. And okay, well, so this angle over here is also dot because of angles in the same segment. So if you imagine this chord here, you're subtending that angle at the circumference and you're subtending that angle at the circumference. So that's also a dot. And then yeah, this is aimless wandering. I just want to disclaim that up front. I have no idea where I'm going. And I'm wondering whether it would benefit me to make this diagram a bit bigger. That would probably be great for me. Okay, but anyway, let's stick it out for now. So I'm just going to try fill in as many angles as I can. Okay, and I've also decided that I do want to make this diagram bigger. So what I'm going to do is what am I going to do? Okay, what I'm going to do is I'm going to duplicate this page, and then I'm going to crop a little bit of stuff. I'm going to rub some of this out. Yeah. Okay, I'll write this out somewhere else. Okay, just going to make this large and large. Okay. Okay, then I'm going to fill this stuff in again. So this is a 90. This is a diameter. Okay, we also know that these two are equal. And I also showed that this is also a dot. Well, I can't wait to do this gray highlighter. This is also a dot. This is 90 minus dot. And so is this, by the way. If it isn't too messy to put that in, you would do that with a pencil. This is also 90 minus dot. This will then be 90 plus dot. And okay, we know that these two are equal. Okay, so I mean, Okay, so remember the train of thought I was on was, well, AC over 2 is the same as OC, and AB over 2 is the same as OF, right? And so the DF times FA, remember I said I suspect that, okay, well, essentially we're trying to show that FC times, so we're trying to show that DF times FA is the same as FC squared, right? And FC squared, well, FC times FC would be the same as FC times EF because these two are the same in length. So if you said FC times EF, it would be the same as saying FC times FC. So essentially we want to show that this line is the same as this line, is the same length as that line. Right, so that was an exciting breakthrough, but I don't know if it does anything for us really. Okay, it was also a lot of exciting scribbling that is now blurring my vision. Thank you. How could we do that? How could we show that they're the same? We could show that they're the same length. We could do that by showing that they are similar. If we could find that there's not even just similar, but congruent, but I don't think it's possible for them to be congruent because I can't imagine that this length here is the same as the diameter. Otherwise our circle would look weird. I think the circle is furthest apart at a diameter. What? 2 points on a circle are furthest apart if they are if they make the diameter of the circle. And there's a video where I've spoken about this, but I forgot which video that is. But yeah, let me know if you want me to link it and I will. Anyway, so but maybe we can show that they're similar. Maybe we could find that they're similar. Let's see. And they are. Oh my goodness, they are similar. Because we know that these two are the same. These two will be the same because vertically opposite. And so therefore these two will be the same. And so we might be able to show that DF times FA is the same as FC times FC by setting up the system of the proportions of the proportional sides. So let's see if we can do that. Okay, so this is unnecessary. This is also not that deep. And this is also not going to be necessary. Okay, so I'm just going to park this because we'll need it a bit later on. Okay, so I'm gonna say in triangle AFC and triangle EFD, okay, we know that angle C1 is equal to angle D because angles in same segment. Okay, right. And then we know that angle AFC, so this guy, is equal to angle EFD, because they are vertically opposite. Right, and then finally angle A1 is equal to angle E, and that could just be third angle, or it could be angles in the same segment again. Right, so let's just say third angle, shorter to write. And so therefore triangle AFC is similar to triangle EFD. And the reason for that is angle, angle, angle. Right. And now we can say, therefore, AF over EF is equal to FC over FD is equal to AC over ED. Okay, and let's see which ones are going to be useful to us. Right, let's see. So we've got AF. Just move this down a teeny weeny bit. So AF over EF is equal to FC over FD is equal to AC over ED. Okay, so that means the one we care about is the one involving EF and FC. Let's see. So EF, FC. And we know that EF is the same as FC. So FC times FC is the same as AF times FD. Yeah, which is what we have up here. AF times FD. So what this helps us to do is to rewrite these little terms in terms of sides that are in this triangle, right? And then we can show that, ooh, Pythagoras, this is actually Pythagoras in disguise. So what I'm going to say here is, we know that EF is equal to FC because of line through center perpendicular to chord, and the chord we're looking at is EC. All right, so it bisects that chord. And so as a result, okay, and also I need to stop forgetting to give the reason. Okay, the reason we know this is because triangle AFC is similar to triangle EFD. Almost said they're perpendicular. Yeah, no. Okay, that isn't very clear. That isn't much better, but anyway, it'll do. And so therefore, using this bit of the statement, right, that would mean AF over EF is equal to EF. Well, okay, we want it with FC. We want to end up with FC. So I'll change the EF to FC, and this one will remain FC over FD, right? And then from there we can cross multiply, right? And so we have FC times FC is equal to, okay, and in this question they're using times E, so we'll just do that, right? Is equal to AF times FD, right? In other words, FC squared is equal to, well, and let's write it the way they have it, DF times FA. So DF times FA. Right, okay, and we know that from the previous from our previous workings, and I'm just going to delete this page. Oh, I don't want to delete it because it has information. Okay, I'll just move stuff once I'm done. We know from our previous work that, so I'm just going to copy and paste this, actually. These are my privileges. No, don't cut. Okay, let's try that again. Copy. Okay, so this is what we know from the previous question. And maybe, I think I've made it too big for me to be able to shrink it anyway. Okay, it's fine. Right. Oh, wow. No. Just paste the things. Yes, like that. Okay, so from the previous question, this is what we determined, right? So let's just look at which sides the question cares about. It cares about AC and AB. Okay, so I'm going to focus on this one because it's got the AC and this one because it's got the AB. Right, so I'm just putting this as a bit of a side note. You can say from question B, we know that AB over OF is equal to AC over OC is equal to 2, right? That's the ratio between the sides. And so therefore, AB is equal to 2 times OF, and AC is equal to 2 times OC. And so therefore, OF is equal to AB over 2, and OC is equal to AC over 2, right? And so we can use that to replace these guys, and we also have a replacement for that guy. So how shall we do it? We shall first copy the thing. Okay. Well, okay, just need, and so therefore AC over 2 squared minus AB over 2 squared is equal to is equal to OC squared minus OF squared, right? And maybe a new line will help. And OC squared minus OF squared, okay, OC squared minus OF squared, according to Pythagoras, will be equal to FC squared. Okay, so that will be equal to FC squared because Pythag said so, right? And then on the other hand, we have shown that AF, well, DF times FA is the same as FC squared, right? Which is equal to DF times FA, right? Which we proved over here. Right, FC squared is equal to that. And so we have proven what is required, which is fantastic. Okay, right. Let's see what how the memo went about it. Okay, so I'm just going to be quiet because I think when I read it out loud, it's just Confucius. So yeah, you'll just have to bear with the silence for a little bit, okay? Okay, so yeah, an interesting approach that they take is they just simplify this expression first, right? So what they do is they just say, well, AC over 2 squared minus AB over 2 squared is equal to AC squared over 4 minus AB squared over 4, which is the same as AC squared minus AB squared over 4, right? And if we just look at that AC squared minus AB squared, we are AC squared minus AB squaring, which is equal to BC squared, right, because of Pythag again. So that is equal to BC squared over 4. But we know that BC is 2 times BC is 2 times FC because of the similarity between the two triangles. So that is 2 times FC, and we're squaring that, and that just becomes 4 FC squared over 4, which is equal to FC squared. So they first show that this side is equal to FC squared, and then they go and they prove like we did, the similarity between these two triangles, so that they can get to a place where they say that FC squared is equal to that. And so because FC squared is equal to the left hand side and FC squared is also equal to the right hand side of this identity, if we can call it that, then we have proven that these two are equal. So that's an interesting take. Ooh, sorry, I was about to fall over. Yeah, their second approach is not too different in my opinion. Yeah, the second approach feels more like what we've done here, our approach to, well, my approach to this question. Yeah, so not a horrible question. I think that when we see a question where there aren't numbers or a lot of numbers, we freak out a bit. We can freak out a bit. But I think that the key thing for me was to kind of pay attention to the build-up, yeah, I think the recognizing the proportion factor was the biggest key for me, because then immediately when I saw in this question AC over 2, AB over 2, but then we're making it equal to, we're checking if it's equal to DF to FA, it felt like this triangle is too distant from the sides that are on the other side of the equation. Whereas OFC, at least there's a common side, or not a common side, but like just geographically. It looks like it might have something to do with DF and FA, right? So yeah, it immediately just came to mind that AC over 2 will just be the same as OC, because we know of that proportion factor that connects the small triangle to the big triangle. AB over 2 will also then be the same as OF, and then from there, yeah, and things like the perp line to chord, those things don't just get dangled for free. Like, there's often a treasure trove. So I guess that was also like something that put me on alert just from the beginning of the question. When I saw that this guy is in the picture, we're probably going to need to use the fact that it bisects this chord somewhere. It might not always be right in those intuitions, but they might help. Anyway, I hope that this has been a good video, and yeah, catch you another time for another chat.